Sir, sorry, sir. We were in a meeting, sir. Sir, please continue, sir.
So now it's okay?
Yes, sir. Yes, sir. Please continue, sir.
So you can hear me and see me, right?
Yes, sir. Visible and audible, sir.
Achha. So I have to share some document.
Yes, sir. You may, sir.
I'll minimize. Share. Achha, share screen. Share. Labor minimize. Labor yeah. Can you see the screen?
Yes, sir.
Okay. Just a minute. Just a minute. ঠিক হয়ে গেছে সব, হ্যাঁ শুরু করছি। Okay. So good morning. Sorry for this 3-4 minutes delay. So Prem, Sukriti is there or she is in a meeting?
Sir?
Is Sukriti there? Sukriti is around.
Sir, I'm checking, sir.
Tell me when I should start. Because I don't want anybody to miss who want to participate.
He is not there, sir.
That's fine, no issue. So should I start?
Sir, we may start, sir. We may start.
Because I don't want anybody to miss, because now I'm getting deep into algorithm courses. So, okay.
Yes, sir. We may proceed, sir.
Okay. So, good morning. So we start from where we left in the last session. Now, as you understand, gradually we are getting deeper and deeper into the subject. So I would request you to kindly listen to me very carefully and try to understand what we are going to deliberate upon during the class, during this deliberations itself. If you have any questions, don't hesitate to ask. Generally, I prefer to answer the questions in the beginning of the next class, because otherwise it interrupts my flow of, the way I plan to talk. But no issue. Please, I'm saying again and again, listen to the whatever I'm saying very, very carefully. Okay. So today, in the last session, we had introduced the name dynamic programming. Probably you have noted that when we most of the algorithms we have discussed so far, Prim, Kruskal, Dijkstra's algorithm, all those are termed as in the category of greedy algorithms. That means the design methodology is greedy. By the name greedy, it means basically you depend on your intuition. You feel, you think intuitively that this is how we should proceed, and then we proceed. But it does not guarantee optimality. We introduced in the last session the name dynamic programming. Today, we will build upon that. Dynamic programming is a much more methodical way of designing an algorithm. You can apply it anywhere in life, whenever you find some problem. And you are supposed to design an algorithm for solving the problem. And remember, we had introduced the data structures, array, stack, queue. And what queue you have? first in, first out. Stack is last in, first out. So you stack one after another in a place. The one you stored at the last, you get it at the first. First of all, in order that the methodology of dynamic programming can be applied to solve any particular problem, it must satisfy several characteristics. You cannot apply the dynamic programming anywhere because the problem structure has to satisfy certain characteristics. What are those? Existence of some sub-problems with exactly similar structure. When we are supposed to compute factorial n, say factorial 6, what is that? 6 into factorial 5. So basically, computing factorial 5 is a sub-problem for computing factorial 6. Factorial 4 is a sub-problem to compute factorial 5. So the problem structure should be such that there are sub-problems with exactly similar structure. Number 2, the smallest sub-problem can be solved trivially, or the solution of which is already available. As I said, for factorial 6, you have to get factorial 5, then factorial 4, then factorial 3, and then finally factorial 1. Now, factorial 1 is 1. We know that. So, the idea is right from the original problem, you go deeper into sub-problems and keep on storing those sub-problems in a stack, and then take it out one at a time. These are known as push and pop operations in a stack. Push means you are pushing something in the stack. Pop means you are taking the item out. But you can pop only that item which is at the top. And the third criteria is the intermediate results have to be stored. So for solving factorial 6, we need to solve factorial 5, factorial 4, 3, 2, 1. And then naturally 1 comes at the top. When 1 comes at the top, we take 1, and then factorial 2 we can compute 2 into factorial 1, and then factorial 3, factorial 4, factorial 5. So we keep on pushing and then popping using the stack operation. Just a moment. Okay. So these are the 3 characteristics a problem must satisfy in order that dynamic programming can be applied. So I've given that example, and this is known as recursion. In implementation or design methodology, this is also known as recursion, which is used in conjunction with stack. Okay, so then another example, think of the Tower of Hanoi problem. We discussed it much earlier in one of our sessions. So just for recapitulation, what is Tower of Hanoi problem? We have 3 towers. To start with, in the initial tower, I, we have a set of n circular disks stored in such a way that the disk at the end is of largest diameter. So gradually you go up with disks of smaller diameter. The problem is to shift this entire set of disks from tower I to tower F, final tower. And we can use one intermediate. We can use one intermediate tower at any point of time. At any point of time during the process, a disk of lower diameter cannot be below a disk of any higher diameter. That is the constraint. We cannot have at any point of time, we cannot have at any point of time a disk of lower diameter below a disk of higher diameter. That is the constraint. We have discussed this earlier. Now think in today's perspective. How do I solve the problem? If I know how to shift n-1 disks to F, suppose I know that, but we have to add one more, say the nth one. How do I proceed? We assume that 1 to n-1 we know. Just like in factorial 6, we assume that we know factorial 5, or the is the same thing. We assume that. So in that case, what do I do? This n goes to temporary tower, and then entire block of n-1 towers, disks, we shift it to F, because we assume that we can do it. And then the intermediate tower mein jo chota disk tha, we shift it to the final tower. And then our job is done. So we need 3 steps. Disk 1 goes to temporary tower. The set of 1 to n-1 goes to final tower. And then the one from intermediate tower goes to the final tower. So in 3 steps, we can do this. Now, we have to solve for n-1. In the similar process, if we can get the result for n-2, then I can get it for n-1 and go like this, exactly the way we did it from recursion. The sub-problems we push in the stack. Finally, we come to 2 disks. So if it is 2 disks, how long it will take? Upar mein jo chota hoga, we shift it to I. Larger one we shift to F. And then this small one we shift to F in 3 steps. And once with 3 steps means 2 to the power 2 minus 1. That means 2 to the power n-1. At any point of stage, the number of steps is 2 to the power n-1. And then we keep on popping 1 step at a time. And finally, I get the solution. Again, the crux of the problem is, our problem was for n disks, but the problem for n-1 disk has the exactly similar structure as for n number of disks. And we know the base solution for the base one. And also we store the intermediate steps. So this is basically prelude for today's session. Now let's get down to another very important concept, which is known as directed acyclic graph. Okay, we know what is a graph. What is a directed graph? Where each edge is directed. Each edge is directed. And what is acyclic? Graph is such that there is no cycle. There is no cycle in the graph. Take for example, the graph you see in the picture. I hope you can see it in the picture. We have S to A as an edge, S to C an edge, C to A an edge. There are 3 edges, but there is no cycle. There is, but there is no cycle. So if we have a directed graph like this, if we have a directed graph like this, first thing is we need to check whether there is any cycle or not. Whether there is any cycle or not. There are many ways to do it. The simplest way to check it is through using Fulkerson's method. What is Fulkerson's method? We start numbering nodes with increasing values, integers. So we number each edge in such a way that the end node is higher in number than the source node. That has to be valid everywhere. That has to be valid everywhere. But at no point of time, you can have any node whose number is less than the previous node. This is known as Fulkerson's. Okay, I'm not getting into there because we are assuming in this case we are provided with a directed acyclic graph. Now, any directed acyclic graph can be linearized. That means the nodes can be considered to be in one line. Considered to be in one line. The picture is intuitive. You see the picture. You see the first picture as graph, and this is the graph, and the second picture is linearized. This is known as linearized, and this is also called topological ordering. Topological ordering. Now, what is the characteristics of a shortest path? For a path between, we have told it earlier also, for a path between I and j, to be shortest, if path is nothing but a set of edges. So if that path has an intermediate node k in between, that means I to j shortest path has k as the intermediate node. So in that case, if somehow I can reach from I to k, then k to j shortest path will be shortest within I to j also. Again, my problem is to find the shortest path between I and j. There are many nodes. There are many nodes in between. There has to be many nodes because it's a big graph. But somehow, I know that the shortest path between a node k to j, that is the shortest path. So if somehow I can go from I to k by the shortest path, then I don't have to reinvent the shortest path between k to j. That would definitely be within the shortest path between I to j. I've given you one example also. Suppose you want to go from MAKAUT in Salt Lake to airport. We need the shortest path. But I don't know the shortest path. But I know the shortest path, say from city center to airport. I know that. Now, if I can find the shortest path between MAKAUT building to city center 2, and then follow that path and reach MAKAUT 2, city center 2, I don't have to think of computing the shortest path again, because it is assured that that solution for the sub-problem will also be within the solution for the entire problem. But in the process, I am minimizing the vastness of the problem. Just like for factorial 6. I know that if I can get it for factorial 3, I know that would be within a part of my computation for factorial 5 or factorial 6. It is also exactly like this. Exactly like this. Now, just see this, the way we have drawn the graph, it is intuitively obvious. I don't think I have to explain it. That so you keep on say what is the distance from A to E by shortest path. Just see, compute this way. I can go by A, C, D, A. So for that, what is the shortest path between D to E? This is 1 plus 1, 2, and that is also 2. We can take either one. From C to E, I know what are the paths available. I can know the shortest path. So from S, I have to go to E. If I did not have to go up to E. If I know the shortest path between S and A, and then A to E, then it would be the shortest path between A to E through A. And we can keep on extending it further. We have already discussed Dijkstra's algorithm. We have already discussed Dijkstra's algorithm to find shortest path. That was a greedy algorithm. What is the difference between the two? Try to understand very carefully. If you remember Dijkstra's algorithm, how did we proceed? Say we start from S, start node, and first go to the nearest node. That means I go to A. And then I consider S and A together, and then go to the node which is nearest to either S or A. Now it would be C. Now we have S, A, and C in our set. And we build up. Now we have S, A, C, these three together. So what is the next node? We go to, so S, A, and C, S, A, and we see, I missed one point. We S, A, initially we had S, A, then we have S and A. We consider any other node which is closer to S than whatever we have already. Closer to S, which is what we have already. That means I go to from S to A. S and A together. What are the nearest nodes now? C for A and B, D for C. But we still have one as the shortest node. So we don't consider this path at all. And this way we build on. That was a greedy algorithm, clearly greedy algorithm. You can note down this graph and these two pictures, and after the session you can try it yourself. But Dijkstra's algorithm is very famous, absolutely very famous. But in Dijkstra's algorithm, what are the salient features. We have not stored intermediate values, and also we have not taken advantage of these characteristics of having exactly similar smaller problems, and also since we have not stored intermediate values, sometimes we may have some problem like this. We'll discuss maybe today or some other next day here. Sometimes just solving the shortest path is not enough. You'd appreciate, by shortest path I mean by distance, say by distance. In many cases, the path length is defined by the number of hops. How many hops it goes through. Just like, say from wherever, from Garihar, you want to go to Howrah station, then you may not be happy just by the shortest path alone. You may be also insisting that the path cannot go via more than 5 crossings or 3 crossings. That means more than 3 or 5 hops. So where we need to find the shortest path from source to destination, with the constraint that there cannot be more than 2, 3, 4 n number of intermediate nodes. That kind of slight variations, this Dijkstra cannot handle. But just looking at the linearized directed acyclic graph, the way we have done it here, it's cakewalk. S to E, what is the shortest path following B? No issue. What is the shortest path following A? Because all the intermediate results are also stored. I hope we are clear. Now, we will consider even a much more complex problem. You have a sequence of numbers, integers in non-decreasing. I should have used non-decreasing, not increasing, because in my example I have 2 6s. So they may be same also. It should be non-decreasing subsequences. These kind of working with sequence matching, then increasing, decreasing, and all those, these are hugely used in genome sequencing. Then today we talk about all kinds of sequencing issues, and this is an extremely complex problem. Why? What is the problem of complexity? Let's take the simplest problem. We have a sequence of integers in non-decreasing order. Instead of saying increasing, I'm saying in non-decreasing order. And our problem is to find the largest subsequence in that string in non-decreasing order. Largest means subsequence with largest maximum number of elements. Like here, we have 52863. You can see 589 is a valid subsequence. Then 23671 valid subsequence. So any subsequence drawn from this sequence with integers which are in non-decreasing order is our feasible solution. So you remember, we have tried to explain, once we have a solution, we must have understanding about the feasible solution, and then we have to think of optimal solution. So any sequence, say 6, 6, 7, is a feasible solution, but not necessarily optimal. How do I get into that optimal solution? How do I go by brute force? Think of some greedy algorithm. Extremely difficult, even for greedy algorithms. How do you start? How do you start? If you start with this, intuitively, you start from the smallest integer. This not necessarily give you the largest, even if say you start with 2. Fine, this is the smallest. Then do you include 8? Do you include 6? They all can be included in the subsequence. If you include 8, you cannot include 6 anymore. If you include 6, you cannot include 3 anymore. So, constructing a greedy algorithm to solve this problem is practically impossible. What are the options left? Think of exhaustive enumeration. Exhaustive enumeration. What is exhaustive enumeration? Think of all the possible subsequences. All the possible subsequences, and then verify each one first, whether they are in non-decreasing order, and then finally you come to your solution. But can you imagine the complexity? Say if we have 3 integers, how many subsequences can be formed out of 3 numbers, just 3 numbers? Say 2, 5, and 3. Say 5, 2, and 8. Just 3 numbers. How many subsequences we can form? 1, 5, 1, 2, 1, 8. 5 itself is a subsequence. 2 itself is a subsequence. 8 itself is a subsequence. So that makes 3. 5, 2, 2, 8, 5, 8. That makes another 3. 3 plus 3, 6. Then 5, 2, 8, another one. 6 plus 1, 7. And 1 null set. Let us assume null set. Jisme kuch nahi hai. So just for 3 integers, just for 3 numbers, we have 8 possibilities. 2 to the power n possibilities. In the problems involving sequences and subsequences, we have millions and millions of characters. Can you imagine what would be the value of 2 to the power 10, 2 to the power 50? So even if we think of solving by exhaustive enumeration, just not possible. Even the largest supercomputer also cannot solve it in feasible amount of time. So now we are doing a smart way. What is that smart way? And again, it is intuitively obvious. We are converting this structure of the problem to a acyclic graph, directed acyclic graph. And directed acyclic graph, these are the nodes, and whenever end node is larger than source node, we draw a directed edge. Like from 5, we have directed edge to 5 se kahan tak ja sakte hain? 8, 6, but not 3, 6, 9, and 7. Similarly, from 2, we can go to one of the places we can go. From 8, we can go only to 9, and like that. Only to 9, and like that. So just satisfy yourself about the construction of the graph. And now, the moment we have the graph, we proceed linearly. We proceed linearly and mark the nodes accordingly. And we know in this process, we know we can easily figure out that 2, 3, 6, 9 would be the 2, 3, 6, 9, not this 6. If we take this 6, it's gone. From 2, we'll come here, and then we have to go straight to 7. But 2, 3, 6, 7. This is the longest subsequence. This is the longest subsequence. Again, the issue is the same thing. Once I keep on building the graph, I start from 7, move backwards, and then at each stage, we store the intermediate results. At each stage, we store the intermediate results. What are the intermediate results? If we think about 2, in the process, we know that there is no arrow here. That means any subsequence, if it includes these 2, will not add anything in the subsequence. On the other hand, this 8, if we come to 8, we have 5 and 2. Either of the 2 is sufficient. So if moving backwards, we always move backwards. Moving backwards, if 8 is in my subsequence, then as well 5 or 2 also can be added in my subsequence. So just like that, from 7, there's no point in coming to 7, 9, because it cannot be there. But from this 6, I have a graph, I have an 8. So if my subsequence with 7 at the end has this 6 before that, then this 6 might have been reached this way, or this way, or this way. So this 6 has so many, I can come to 6 here through all these 3 ways. Which way I will follow? Which way I will follow? Because if I go to 5, I add only 1. If I go this way, this is one way, and this is another way. If I go via 3, I can have some more things. So once we move backwards, and since all the intermediate values are stored, so the final result we can compute. How many computations we have to make in this case? In the previous case, we saw for exhaustive enumeration, 2 to the power n. Exhaustive enumeration is 2 to the power n, which is physically not possible, even for the largest supercomputer. Here, how many? For each node, I have to have how many? Basically, I have to draw the graphs. I can have n, and for each of n, in the worst case scenario, I have another n. So it would be of n square. Right from 2 to the power n, I come down to n to the power 2, and now it is very much feasible. Just think of if the number is 20. What would be the 2 to the power 20? Just think. Because we know the values of 15. 2 to the power 15 is how much? 32768. So if there are 15 things and we go for enumeration, exhaustive enumeration, we have to verify with 32768. So many variations. And in this case, it will be worst case 15 to the power 2, that means 225. Just see the reduction in the number of computation. This is another beauty of dynamic programming. In many cases, in the previous case, I did not explain this, this shortest part thing. In the short, I am not going into analysis as such, because that involves too much mathematics. In that case, in the shortest path problem, Dijkstra's algorithm also takes n square. My dynamic programming DAG also takes n square. So we do not gain much in terms of complexity or timing to solve the problem. Whereas in this case, we have, like this case, there will be many examples. There will be many examples where by using dynamic programming, I can bring down the complexity of the algorithm very significantly. Some problem which was so far unsolvable, now we can solve. Now remember, I always tell my students, you cannot gain anything in life without losing something. Philosophically, I always say my young students that whenever you gain something, there is no need to be too much excited, because it's sure that tomorrow you will be losing something. And similarly, if you lose something today, need not have to be absolutely saddened, because tomorrow you will gain something. Everything is balanced in life, everywhere, in every dimension. Conservation value is everywhere. So here, we are gaining time. So what we are losing? Of course, we are losing space, because now we have to store all the intermediate results. Since we have to store all the intermediate results, dynamic programming will require huge number of intermediate storages. I give you, and this in practical life, we use this example many times. Well, what do you do? Suppose you move out with friends to some places. You want to visit some place somewhere. You want to go to some North India, some place, some vague place, not that well known. One way is from here itself, from Calcutta. Say you want to go to Manali, fine. From Howrah, you want to go to Manali. From here itself, you can draw the entire path. Other objective is, okay, instead of thinking about that, let's go to Delhi first. वहाँ जाके पता कर लेंगे. That means entire information for going to Manali from Delhi is available there. Or you go to Lucknow, or probably you go to Hardwar, or you go to somewhere else. So instead of concentrating our energy and efforts for solving the full problem, we concentrate on solving a sub-problem, and knowing fully well that the remaining part of the problem will have the similar kind of structures as for the entire set, as for the entire problem. But be very careful about that issue. It has to have exactly similar kind of structures. Counter example. Suppose you want to go to Badrinath and you want to go by car. Fine, no issue. From Delhi, from there, you want to go by car or by train. Fine. So you go to Hardwar, and वहाँ जाके you find the route. You solve the problem without solving the problem before leaving home. But now, if you use the same methodology for going to Kedarnath, you have a problem, because there, the last 16 kilometers, you cannot travel by car. So I hope you appreciate, because going to Kedarnath, there the sub-problems do not have the exactly similar structures, exactly similar structure for the entire set of problems. Again, because that is an example of social science. But again, if your team is not bothered about roadable, motorable road or walkable road or whatever, then the nature of the problem is same. No problem. So when we say they have the similar structure, they have the similar structure, you apply it to some exact science. We are discussing about exact science. Most physical sciences, mathematical sciences are exact science. There, it's relatively simpler. But when you apply the similar kind of problem solving methodology for a social science, issue in social science, then just the example I am given, moving from Calcutta to Badrinath and Calcutta to Kedarnath, you cannot consider all the sub-problems are same as the original structure. But you can consider that same if the person who is going does not bother walking or does not bother about taking a road or whatever. But I am emphasizing again and again, the beauty of dynamic programming is through this methodology, you have all the options in front of you. You don't have to solve the entire problem to start with, but you have to store the sub-problems, results of the intermediate sub-problems in those intermediate stages. But this longest increasing subsequence is again considered to be a very, I should say, studied subject in algorithm design because of its, it reveals so many interesting features. Straight away decreasing the computational complexity to such a level, giving you the options of giving you all the options in front of you and all those. Okay. Now, this is what I had been saying earlier. In many cases, we have to find shortest path with upper limit on the number of intermediate edges. Path is a collection of edges, and intermediate edges and intermediate nodes basically synonymous. So this is a simple graph. This is a simple graph, and just see, I'm interested to go to T from S. I'm interested to go to T from S. There may be other paths also. I have just intuitively or manually found out some of them and computed the total distance. So if we consider only distance as the metric for computing shortest path, then S, A, B, D, T cost is 5. But we have to go via 3 intermediate nodes. On the other hand, if we go via S, D, T, just 6, but we go through only 1 intermediate node. In many, I should say in almost all examples of networks involving electronic computation, distance doesn't carry much of a meaning. It's only the intermediate nodes. Those are absolutely important. Say through mobile, say you want to talk from Salt Lake to CR Park in Delhi. Talk to CR Park in Delhi. Then how the routing is done? It will go to the nearest tower, and in between it will go via several towers. It may also go via satellite. It may go via whatever. It may go via optic fiber, so many things. But major time wasted is in the towers or in the intermediate nodes. Physical distance doesn't carry any meaning because the electronic signal move at the speed of light. So the distance, so there the number of hops are absolutely important. Number of hops are absolutely important. So how do you, so the most of the time the problem would be find the shortest path between S and T with the constraint that in between there cannot be more than k number of nodes, more than k number of nodes. Think about our previous dynamic programming approach. We can do it like that. In fact, these can move to another serious class of problems, which are known as multivariate optimization problems. Those are hugely complex problems in mathematics, but they have many applications as well, where you have to optimize with two variables. Generally, we have to optimize one variable, but in many cases, you have to take care of two variables. Like I am going out, I have one suitcase, I have to include my everything there. So there, what are the items to be taken? Cost is one variable, weight is one variable. So that the optimization depends on combination of many variables. How do you come to a solution? So here again, remember, we discuss about optimization problems, and also we need to have some idea about decision problems. So optimization problem is having given the problem, what is optimized value? In many cases, it is very complex, but we may have some idea about what should be the optimized value. But what is the decision problem? Somehow, I think that this could be a feasible solution, and test whether this solution satisfies all the constraints or not. If it's okay, fine. If it's not okay, I take another decision problem, another solution. There it is much easier to handle. Very common example is when you go for marketing, you want to buy a TV. You have the parameters and etc., and you have some clear idea about what is should be the optimal cost. Optimal cost. This is say 50,000 optimal cost, but it needs huge amount of searching, huge amount of efforts. Somehow we think, why don't you try? Let's go to Garihart and see what is the price. You go to Garihart, you get a TV at 48,000 with the same parameters. Fine. You say that I can take it. No. So here, your optimization problem is converted to a decision problem. If you are not happy with Garihart, you go to some other place and again see that whether this is fine or not. So two issues. One is you are converting your ultimate objective from optimality to satisfiability. Optimality to satisfiability. And you are not that hard and fast stringent about optimality. But you have some idea about what the optimal solution should look like. some idea about what the optimal solution should look like. But in exact science, they will not accept this. They will go for the optimal solution, and there they have a function which represents all these multivariate of the objective functions. And then once we have this, we have discussed a lot on shortest path analysis. Ultimate objective of all such discussions is to have a framework where, having given a road network, how do I know the shortest path between any pair of nodes? So far, we have been discussing about two nodes. Our ultimate objective is a town planner. In Calcutta, it's a big city, complex network. The police commissioner in or the transport secretary, he will have one complex network, and together with that, he would like to have complete information about shortest path between any two nodes. And then shortest path between any two nodes with constraints. That means shortest path, but not involving more than two, more than three, more than four, these kind of nodes. In that case, if some VIP movement, some ambulance, some fire brigade movement, if there is a shortest path between X to Y, but beach may there are, say, 10 crossings, that will take a lot of time. So to facilitate the movement process, practically while they will convert those crossings to one way. You have seen this during VIP movement. When generally it is a crossing, but for VIP movement, this does not act as a crossing. One side is blocked. But then again, you have to have all kinds of considerations. What route would be better? It depends on traffic and everything. But the basic data is I must have in front of me the complete graph and at the same time, shortest path between any point to any point, and also shortest path with, say, I use a decision support system. These are supposed to be taught in software engineering classes. Whenever you develop a software with algorithms, there are basically two types. One is management information system, where the software gives you the answer, like payroll statement, profits and loss account, balance sheet, and all those. And the other is the decision support system, where the software helps you in taking the decision. When you take the decision, play with the software, but you take the decision. So that for the same software, you can take one decision, I can take another decision. So in routing schemes, both are possible. Mainly in physical transport networks, looking at that, at some point of time, I want to see, say, from these 10 pairs of nodes, what are the shortest possible path with not more than 5 crossings, 3 crossings, 4 crossings. And then there are some other variations of network problems as well, very closely related to this our everyday life. So when we talk about I don't know where that has gone. At some point of time, there was huge media coverage on some project called smart cities. So once you say smart cities, these are some of the characteristics a smart city should have. Sitting in Newtown, I want to go to Joka. The way sometimes driving directions that make, the Google driving directions and all those they give. This is what they do. I want to move. So what is the shortest path? By time, by the number of nodes. But at the end of the day, we have tried to introduce the beauty of dynamic programming, but again and again, it cannot be applied everywhere. It has to satisfy, the problem has to satisfy certain characteristics. Otherwise, dynamic programming cannot be applied. I am deliberately avoiding the analysis part because already some have to get into some mathematics, and analysis part is highly mathematical. So if some computer science and IT students are there, they must be having a regular course on design and analysis of algorithms. So I'm not getting into that analysis part. But at the same time, I'm trying to make you understand the underlying the beauty of problem solving using algorithms. What are the different methodologies? We have so far discussed greedy approach. Today we have discussed dynamic programming approach. Probably we have to have one more session on dynamic programming approach, because here most of the participants, most of the students, they have still some confusion about dynamic programming approach. And then there are other methodologies also like backtracking, branch and bound, and all those. So we'll keep on discussing that. I hope you are enjoying. So I think that's it for today. So anybody there? Prem?
Yes, sir. Yes, sir.
So I think in the last class, I thought it was too heavy. So today, I tried to move a bit, but still, I tried to cover whatever I wanted to cover today. Anything beyond this might be, one should take something which can be digested. But I tell again and again, since I am not giving any notes directly, please ensure that all these lectures, all these talks are available in the web. Huh? Prem?
Yes, sir. Yes, sir. It will be available.
Otherwise, it would be difficult for the students to follow.
So it will be available, and probably we have uploaded almost 60 to 80% videos, and so, still 1 or 2 videos is left, and it will be up.
So that can be available, that can be accessed in YouTube?
Yes, sir. Yes, sir. It can be accessed, sir.
So would you please send me the link?
Yes, sir. Yes, sir. Sure, sir.
Because the slides only contain very small gist part, but yes, the talk is also important.
Yes, sir. Sure, sir.
And this is the problem with online classes. Please encourage the students to ask questions. Otherwise, I don't know.
Yes, sir. Sir, we may have a short quiz. We can make a short quiz of 4 to 5 questions in the next class, and we will share it via mail to everyone.
No, that is the problem.
Yes, sir.
I believe the quiz should be set by the students, not by the teacher.
Yes, sir.
The ideal purpose of a teacher is not to answer anything, but to motivate the students to question.
Yes, sir. So then we may take 2 to 3 students, and we may ask that how they are liking the video, the lecture sessions, and based on their recommendation, we will put some questions.
No, let them ask questions.
Yes, sir. Yes, sir.
Let them straightforward. Let them ask questions.
Dear students, if you have any question, then please come forward.
That's what I'm. But if they feel happy, no problem. But these topics are very much.
Sir, I was asking, sir, that we may have a small quiz for the students, so that they can get more attractive for these sessions. They can answer some questions.
I told right from the beginning.
Yes, sir.
This session is not meant for getting marks.
No, sir, not for masters. It is for generally general purpose, sir.
So that's what I'm saying. They can have many books. Get preparation books are available, you know. So I'm sure they're having some regular classes for analysis design, data structure algorithms, and all those, right? So since even though the topic of this session is the role of algorithms in problem solving, probably have noted that I'm covering from a much bigger canvas using data
Yes, sir,
structures and
exactly, sir.
using data structures. Maybe at some point of time I'll be using some databases also, because so far we are discussing only computing intensive algorithms. There could be many data intensive algorithms also. There are, no? So let us see how it goes. So I hope.
Yes.
And when do you have the exams? It's still quite some time. No? I can plan for another 5-6 sessions as
Yes, sir. We are with you, sir. Whatever session you want to take, you can take, but we can check out whether the date will be available or not. Otherwise, we can shift time
okay,
slot. We can shift some
okay,
time slot if not available.
okay, okay, okay. That's all for today. So next class, next Thursday, 11 o'clock. Huh?
Yes, sir. Thank you, sir.
Okay. Thank
Dear
you.
participants, thank you for joining this session. And the next session will be on next Thursday at same time. So till then, please stay connected with us. Thank you for joining the session.
Thank you.
Thank you, sir.
Thank you.
Sorry, sir. Today there was a meeting, sir.
No, it's okay. But only thing is, please mail the link at least in the previous night. Otherwise, we feel,
Yes,
try to send the link in the previous night. Huh?
yes, yes, sir.
Okay.
Yes, sir. Yes, sir.
Okay.
Sure, sir.
You are doing a good job. Thank you.
Thank you, sir. Thank you.